Hello, hi, this is the third video for control system lectures. I hope you've been following up with the first two lectures, and because you will not be able to understand this if you didn't go to lecture number 2 specifically, which we derived the system model for an RC circuit. And I won't be going through that now because I had to now find out the system response of the system model. So yeah, let's do it. Let's get on to it. Let's bring up the circuit. This is the RC circuit. Let's bring up the system model which we derived. I believe this was the equation v dot t plus AVT equals BVS t. Yes, and yeah, VST is the supply voltage, VT is the capacitor voltage, and the derivative of that. And yeah, this is the equation. Now what this is a system model, so to get the system response we use Laplace, convert this ordinary differential equation into this format, some function of time. Okay, then let's begin. Now I won't be going through in-depth Laplace. I will just skim through this very quickly because I told you I will not be teaching you basics. Maybe in another video I will teach you Laplace, but this is a summary video, so I hope you can keep up. Laplace of this first derivative. It's a first derivative equation. Go to the differential. Okay, this is blocking the Laplace table. Let me get rid of this. Okay, the first derivative, it's a differential equation. So what I'm going to do now is to find the Laplace of this. Okay, v dot t. Now go to the differential part. Now v dot means n is 1, first derivative. So n is 1 is this fs becomes vs, by the way. This f is v because this is a very generic format. So this f is v, n is 1. So s to power 1 vs minus s to power 0 v0. Very simple. Okay, we don't have to put s to power 0, we can get rid of that. So it's just simply s capital V s minus v0. Okay, this is the Laplace of this. So and oh oops, let me write that a little lower. S capital V s minus v0 plus a, and this is a variable. But how to find the Laplace of variable? Ft. So v is going to be vt, and Laplace of that is vs. Very simple. Capital V s equals b. Over here it gets a little tricky. Now VST is the supply voltage. I'm going to make an assumption. It's okay to make assumptions. This is mathematics. We can make assumptions. And in this case, the assumption is the battery will not have draining voltage. It will not drain. What does that mean? That means is that battery voltage is going to be consistent. What does that mean? That for DC supply, VST can be written as some random voltage, could be 12 or something, I don't know, into a step input. We can make this assumption. It's okay. We can make this. It's not a problem. So now we have to find the Laplace of VUST. VUST. So what is the VUST now? Into it's a consistent random variable, but UST, what is the Laplace of UST? A step input. So unit step ut, it becomes 1 over s. Very simple. 1 over s. There we go. That's it. Let's go through this. Vs are the Laplace of the capacitor voltages, Vt. V0 is the initial condition of the capacitor, which could be some initial voltage the capacitor had, which is V0. V is the supply voltage, and the step input will help to show that it's a consistent supply input. Yeah, that's it. Very simple. Nothing much. Now let us clean this, and let me clean this equation quickly. This won't take long. Now I'll show you why, to explain to you why it's easy to clean this. Is let's look at in a philosophical perspective. As I told you, mathematics is about philosophy, to understand it from a philosophical perspective. Now what do you notice here? These are all, what is this? So these are actually differential, these are derivatives. In this equation what we have is derivatives, like v dot t, and when you have derivatives it's annoying. I cannot tag these because this is a rate of change of voltage, time, and these are just vt. I cannot tag these together. So derivatives, it's annoying. This is inconvenient for me. But what happens after I use Laplace? After I use Laplace, what I have is no longer derivatives. What I have now is algebraic equation, no derivatives. I can tag these two. It's more convenient. This is the beauty of Laplace. This is the beauty of proceeding to move on to a step system response. So let us now tag these two, s plus a, vs equals, let's take the initial to the other side, plus bv over s. Now let's make vs, which is what we need to find, subject 1 over s plus a, v0 plus bv s plus a. Yeah, that is it. Now actually this is not it, guys. Now this is not in this, how the real world works. In the real world what we have is time domain. This is not in the time domain, this is s domain. So we have to convert this back to time domain. And how do you do that? Inverse Laplace. But before you do inverse Laplace, you have to do something very important. And what is that? Partial fractions. You have now apply partial fractions, because problem here is that in this format it's very difficult to do Laplace, because we cannot find this stuff in the Laplace table. So we have to convert this into a format where you can find this in the Laplace table, and that is with the help of partial fractions. So let us begin to apply partial fractions to this and this. I will not teach you partial fractions right now, learn your basics. I'm just going to get into it and hope you can follow up. So partial fraction, so that is 1 over, actually we don't have to apply partial fractions here, only here. It's my mistake, only here. So 1 over s plus a remains s plus a, no need to apply partial fractions, and over here becomes b over a. My mistake, let me correct that. b over a 1 over s minus 1 over s plus a. There's a secret to doing this very quickly. I will teach you in the next video how to find a partial fraction very quickly. It's a little trick I have. I'm sure some of you already know that, but I will teach you in the next video. But right now I hope you know the basics of partial to know how I got from here to here. Okay, now we have this in the Laplace table. We have this. Oops. Let me hold on quickly. Okay, now we have this in the Laplace table. So what that was is 1 over s minus a and 1 over s. 1 over s is unit step, 1 over s minus a is cos, it's e to power minus 80. But what we had there wasn't 1 over s plus s minus a, it was 1 over s plus a. So e to power 80 plus 1 over s minus a, but here is plus a, so if it's plus, this has to be minus. Simple logic. 1 over s is ut, so that of course you know, and if it's ut step input, we can write it. Now let's find inverse Laplace and you'll understand. Laplace of this, so vs becomes vt because of inverse Laplace, and v0 initial condition 1 over s plus a, again e to power minus 80, go to the Laplace table. b over a constant remains the same. This voltage comes here, this one, it's also kind of a constant. it's the supply voltage. 1 over s becomes 1. We can write the step input that way. It's how we do it. 1 over s plus a again e to the power minus at. Very simple. That's it. This is the system response. Is the system response. But system response of what? RC circuit. And what does this tell you? Let's find out. Oops, sorry. Let's find out what this explains. Give me some time to quickly erase this. I'm still trying to get used to this software though. Okay, and let's bring up the, yeah, okay, brilliant. So Vt is the capacitor voltage of some random voltage and some random time. Whatever the time is, you input, you get the voltage of the capacitor at the specific time. V0, initial condition of the capacitor, what the initial voltage is, A, B, A, and all the constants, and V is the supply voltage. It's the DC supply. That's it. Very simple. And please don't mix up Vt and V and all. It's a common mistake a lot of students do. If I had to write this again, do not mix this up. Vt is capacitor voltage at a specific time. V, capital V here is Vst, which is supply voltage. Okay, do not mix this up. That's it. Very simple. In the next video, we'll go through more complicated Laplace and complicated functions. And yeah, for now, I will be stopping this video short, and I hope you understand this lecture. Yeah, subscribe, like my video if you like it, and please share with your friends so that it will support me well for the future videos. Yeah, thank you for watching.